This is a lecture on metric learning and few-shot learning, and I'm Nikhil. I also have a co-instructor with Ravinder, who I think has joined in the meeting. I'll be walking through some of the basic concepts of metric learning, and some of the things that should be covered in few-shot will be taught by Ravinder. So let's start the problem the by defining what is actually the motivation for defining something called as metric learning. So so let's say we have a different kind of a classification problem in our hand. So you have seen in your previous lecture that a classification problem is the one which the model takes an image and the model is given a label. The model will give a label to that image. That's what is happening in most of our classification problem. Here we are
Nikhil,
dealing with a different kind of
your
a.
voice is breaking up a bit. Yeah, since one or
Okay,
two.
okay,
Yeah, yeah. Now it's fine. Now it's fine. Yeah.
uh, okay. Okay, so I'll repeat what I've been saying. Different from our original classification problem, we are dealing with a different classification problem where we are taking in two images, image A and image B, and our goal of our problem is to classify whether they are same or different. So I've defined some terms loosely, same, different. We'll come to that, what we mean by these terms. But if I motivate that with an example, say for face recognition problem, and we have a image of an employee A, and we have another image of the same employee A, and we want to make sure that in that face verification system, how much similar are they, and we want to allow the access or not, or maybe for a gate entry thing, gate entry based system. So these are the kind of problems which we are actually going to deal in metric learning models. I'll reiterate this in the beginning that it's little different from our conventional classification problems. That in conventional classification problems we are only given one image, and so far you've seen a lot of CNN based deep learning models where the models is going to extract features automatically, so that the features are optimized with the classifier, and the features will be learned corresponding to what the classification problem we are having finally at the end. So if it's a dog versus cat classification problem, the features will be learned according to discriminate between a dog and a cat. Now here the model is going to learn features to discriminate between image A, image B. So it's a
And
little
Nikhil,
different. The
Nikhil,
features the model will be
sorry,
learning.
yeah, sorry to interrupt again. It's happening again and again. The
Yes.
voice, yeah, there's maybe something
Okay.
is hogging your bandwidth in the background, Dropbox or anything, which might be affecting the
I don't
voice.
have anything other open. Okay.
Yeah.
So I'm not audible. Maybe because of my mic. That and see. Am I audible right now?
Yeah.
Okay, maybe because of my microphone. Sorry about that.
Yeah, no problem. Please continue. Thank you.
Yeah. So as we were telling, the metric learning problem, we are dealing with the features that would be extracted in the model will be to discriminate between image A and image B. So the model which we are going to create is something called as a metric learning model, and this is an important problem in computer vision. This is commonly known as the matching problem in computer vision, and it's been used widely in computer vision tasks. So there I might again come back to the same point. We are just asking a yes or no question whether image A and image B are same or different. And the condition or it depends upon the problem statement to define what is similar and what is different. If we are defining a problem like classifying different breeds of dogs, it will be each breed of the dog will be a different breed, different class. So likewise, we'll come to some of the examples and it will be made more clear. So the metric learning model really has to do with something of inducing a similarity measure. So what I mean by similarity measure, and also will come later on in our slides. Basically, similarity measure has to do with something called as distance. If similarity is more, we say that distance is less. So that's the kind of proportion, that's kind of the relation the similarity and distance will be having. So we'll define these terms more formally. So what do you mean by metric learning? Metric learning is an approach based on which we aim to establish a similarity or dissimilarity between objects. See on the on the left side, you can see these are features that are extracted from your MNIST data set, and after machine learning framework is defined and trained, this is the kind of result you're going to get. Each of the colors are going to get are going to be uh,
It's breaking up a lot
are
again.
going to be
We
different.
couldn't. Hello.
Hello.
Yeah, we couldn't hear what you said after the slide started again.
Okay.
It all broke up the voice.
Okay. Okay.
Nikhil, maybe are you
Yes.
using Wi-Fi, right? Wi-Fi at home or somewhere? Yeah, maybe you can. I don't
Yes,
know.
I.
Yeah, yeah.
It's a
You know, a
second.
lot.
I do.
Yeah, your voice is breaking up a lot. Maybe you can reboot your modem or something. It's breaking up a lot.
Okay. So I'm not audible till
You're audible.
what
You're
point?
audible. You're audible, but
Okay.
your voice is breaking up a lot. A lot.
Oh, okay. Okay. Okay.
Can you please go bit slow? Then it will affect less.
Yeah.
Okay. 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 Yeah, I'm again really sorry about that.
No,
Not
no
sure about
problem.
what
No problem.
exactly is the problem.
Yeah, yeah,
Uh,
yeah.
yeah. So just to uh, reiterate what I was telling, uh, the problem we are dealing with is to compare between two images and to decide whether they are similar or not. And by similarity, we are going to define a distance metric. Uh, we will depend upon that distance metric to quantify how much similar both these images are. We're going to ask basically going to ask questions whether this image is similar or different based on the distance metric we are defining. So yeah, so so this is the formal definition of metric learning, that it aims to establish the similarity or dissimilarity between objects. And on the left side, you can see the encoding in a feature space. This is for a classical MNIST problem. Once you're setting up a MNIST metric learning framework, after training, you're going to see the embeddings like this in the feature space, where the similar uh, the digits are going to cluster together, and the different ones are going to be separately placed. So am I audible right now?
Yeah, it is fine.
Okay. Okay.
Yeah, yeah, yeah.
Okay. So now let's come to defining what are distances more formally. So before that, just to give a feel for where exactly is metric learning used. We have a lot of applications. In fact, I've already talked about face recognition apps, face recognition task, where you are given to verify the image between two personals of an employee of an organization, and you are asked to say whether they are the same person or not. That's one of the typical application of metric learning, and we'll probably be able to cover some of the application in few short learning framework also. So we'll probably explore this face recognition task a little more detail in our few short learning session of this tutorial. So another application would be like to check plagiarism. Though we are dealing with the computer vision applications, another one is to point out that if two documents are given and we extract some kind of a feature from those documents to see if they are similar or not. So that's another typical application of metric learning based frameworks. So you've already seen MNIST data set, where you have seen that we're gonna see you recognize some handwritings. This problem can also be reframed in metric learning frameworks, where you see that if you can bound each of those digits and you can compare against uh, the a prototype that has been created in metric learning. So just interrupt me at any point if there are any doubts or I'm not making sense to you. Feel free to do that. So I guess I don't have to repeat any of the things I've said.
Yes, go ahead. Yeah, there is in between there is slight breaking up, but it's fine, we can still make it out.
Yeah, so please interrupt me at the point if I'm not audible of please interrupt me, so I can repeat whatever is the point that that I failed to convey.
Yeah, just slow down a bit, it is fine, we can hear you fine.
So let's formally define what is a metric. Metric is something which has to do with distance. So if we are given two pair of elements, and the elements we are going to deal with are going to be your features that are extracted from images. So these are all basically going to be points in high dimensional space, right? Features are embeddings. Are there going to be some, let's say 128 vector elements, which we are going to extract from your deep learning framework? These are all going to be points in a feature space, in the high dimensional feature space. And we want to establish the distance between the points. So we need to define what is distance in that feature space. So, and by defining a distance metric, we will be defining the measure of similarity between that points. So this is just for formality, but if f of xy is a distance metric for x, y, z belonging to a set, then we have all these 4 properties which we are familiar of, that the distance should always be positive, the distance will be 0, then it implies that it's the same point, and that the distance metric should be symmetric. The distance between x and y should be the same as distance between y and x. And also the triangular inequality, which says that distance between 3 points x, y, and z will obey this inequality, that the distance between x and y, the sum of the distance between x and y, and sum of the distance between x and y and z will always be greater than or equal to the distance between x and z, and the equality will hold if all the 3 points are collinear. So I think these are things which most of you will know, and just to formally define these things, I'm just going through all of these. So let's move on. So we will define different kind of these metrics. So let's say we have your normal Euclidean distance, which most of us are familiar with, where we say that if x and y are vectors or are points in high dimensional space, how do you calculate Euclidean distance? Is by computing this dot product, right? You subtract those vectors, and then you take the transpose of them and you compute this dot product. This is basically computing the dot product, and you compute the Euclidean distance. And we have another type of a metric, which is Mahalanobis.
Oh, I think feed stopped. Abhijit, is the feed stopped for you?
Yeah, it is stopped for everybody. Wait, I'll call him.
Yeah, just ask him to reboot his modem.
Yeah,
that will be fine. Yes, the feed stopped for everybody. Nikhil will reboot his modem and come back.
Okay, I'm facing a lot of problems in my Wi-Fi, and I've tried to connect to some other network also. It's similar. So when I try to connect in my mobile network is breaking my voice. I hope this should work right now.
Yeah. Now you're audible. Yeah, it's fine.
Okay. I don't know how much interruption will happen, but let's go on.
Or you could do one thing. This is your Wi-Fi or mobile network?
Yeah, this is my Wi-Fi right now. I tried it through my mobile. It's my voice is also breaking. So
Yeah.
uh,
This is fine. Your voice is audible.
okay, I have to go on like this, I think. Yeah. Sorry about that. I'm not sure
No
what is
problem. No
exactly the
problem.
problem.
Even I have seeing it in my laptop. My laptop microphone is not good. Now I am talking through my phone. So I have logged in through my phone and laptop. My laptop microphone is not so good. So you could do something like that.
Okay.
So now it is fine.
Uh, okay. So let's continue.
Yeah.
So I'll just repeat. We have a
Just
metric called as
share your screen. Share your
Okay.
screen.
It's not shared. Okay.
Okay. Yeah.
Okay.
Yeah.
So I've talked about Euclidean distance. I think that up to that point it was clear. And we have another metric called as the Mahalanobis distance, which is a learned metric. It is called as learned metric because we are trying to estimate some covariance from the data itself, and we are trying to calculate Euclidean distance. This is also called as a generalized Euclidean distance.
So greater the similarity, smaller is the Euclidean distance. Greater.
Yeah. So great. So distance and the similarity are kind of inversely related, right?
Okay.
So that's a general intuitive idea we are having. So greater the distance in a feature space, less will be the similarity.
Got it.
Yeah.
So can you please explain why it is called learned matrix?
Sorry.
Why Mahalanobis distance is called learned matrix?
Oh, why it is called a learned metric? Okay. So Mahalanobis distance is basically used in those schemes where you have these x and y axis, right? So let's say this is your x axis and this is your y axis. And if there is a correlation between these x and y axis, let's say x will represent the temperature and y is representing something like the ice cream sales that is going on. So as the temperature increases, the ice cream sales will increase. That's a general idea we're having. So when both these variables x and y are correlated, Euclidean distance may not make sense. The Euclidean distance is not considering the correlation between these two axes. So in fact, and some other use cases where the scale of x and y are completely different. X might be dealing with in 1.1, 1.2 kind of range scales, and y will be dealing in thousands. Then Euclidean distance will be biased towards that higher scale. So in such cases, what we'll do is that we are going to normalize the data into, or we are going to transform the data so that it becomes agnostic. So what we are basically going to do is that we're going to take up this x and y axis, and we are going to reframe and rearrange that x and y axis so that the covariance and the correlation in the data is going to be minimized. And then we're going to calculate a normal Euclidean distance. Did that make sense?
That is fine, but I want to know, like, it is also predetermined matrix. Like, if we have a data, we just can get the Mahalanobis distance from there. But
No, actually,
why?
it depends upon the data you're going to examine, right? It's not the M is going to be dependent upon what data you're going to examine, and you're going to calculate that M from that data.
Okay, like we cannot just like Euclidean distance, we can get it from just x and y. We cannot get it from for Mahalanobis distance. Is it?
So it depends upon the problem to problem. So this definition is going to be applicable for every problem, and this M is going to vary between problem, right? This x and y.
Like that. Okay. Continue.
Yeah. So that's basically what we are telling, like Mahalanobis distance is the learned distance. It's also called as the generalized Euclidean distance. So this is an unsupervised framework, Mahalanobis distance based metric. because we are not using any labels to X and Y, XY points. And it's also a linear metric learning scheme, right? Because it's just a multiplication by a metric metrics. So it can't do any non-linear operations.
Okay.
Okay, so let's move on. Let's come to the main interest in the whole session, which is going to be the supervised metric learning framework. So in supervised metric learning framework, we will still have these X and Y points which we need to compare, and we'll also have the label associated with them in the training scheme, whether they are similar or not similar. So how we are doing it in traditional ways, we are going to extract features in traditional machine learning framework, where before the pre-deep learning era, people used to extract features like colors, texture from the input images, hope that they would correspond to okay, they would correspond to make a correlation between whether this X and Y are similar or not similar. And then we'll use a predefined similarity measure to compare between X and Y. Is there a question? Can I move on?
Yeah, I think so.
Just checking. Yeah, just checking whether I'm just staying online. That's why I'm just pausing in between.
Yeah. Okay. You paused. Okay. We thought our feed got cut or something. Okay.
Okay.
Yeah, please continue.
One question.
Yes.
Why normal similarity measures that don't work? Can you explain a bit? Like this kind of texture and color cases.
Normal similarity measures. What do you mean by normal similarity measures?
I mean, before this machine learning approach, this metric learning approach, we used to compare images with their texture and texture, color, and other small features. Those are taking that we are going for the metric learning.
Okay, if I understand the question correctly, can you just type in just to because I'm also having some problem in understanding your question. So I can.
Yeah, please type it in. We also couldn't.
The question is that like why don't we simply take the Euclidean distance between the pixel of the images? Why do we need to extract the features? So that is what he was asking.
Yeah. So the pixel of the images, like say if you have to compare two persons, and you see there are a lot of redundancy in the pixels, right? If this is a hair color, you're having a lot of black colors that are not going to be informative about the final similarity you're going to make, similarity decision you're going to make. So it's the same answer that I would put for why do we need to extract features at all from a classifier point of view. So because we are only interested in features that are discriminative, right? So what our final end goal is that we want to extract, if we are doing a classification problem, we want to extract features that would be good for the classifier. So that's exactly what is happening, that has been optimized through this the advent of deep learning, where the feature extraction is also carried out optimized with the final classification. So in traditional machine learning, we only had this feature extraction, which was disjoint with the final classifier. Now, through this introduction of deep learning frameworks, we do that together. We say that let the feature be extracted and let it be the best feature that will be extracted so that the classifier is also going to be good. Does that make sense?
I have typed my next question in text box. Can you see?
Okay, just a second.
I meant to say if we have like at the end of that this network, we will have a feature metric, right? That
Yes.
we will compare between two images to see whether they are similar or not.
Yes.
Now my question is, if we can express those metrics, these parameters in terms of some mathematical formula, then our job will be much easier, like much more, like faster to calculate those features from the images and to compare. Then we won't need any machine learning network to solve this problem. Is it like that we are unable to find those parameters from normal mathematical formula? Is it?
Yeah, if I say that normal mathematical, if you mean by normal mathematical formula, what do you mean exactly? That you're
Just
going to
like,
extract.
suppose we want interested in measuring distance from for 2 points. We
Okay.
use Euclidean distance. So like that, if we have some parameters, like suppose that is a function of that image pixel value at each pixels. Uh, if we have some function that will give us that transformation from that image to that feature domain, with that feature domain values, if we can again come up with some mathematical formula that will give us similarity measure. If we have that formula, then we won't need any machine learning network to check whether they are similar or not. My question is
Yes.
it like that? They are unavailable. They are not available. That's why we are only doing it with machine learning.
For the applicability of universal applicability, if I understand correctly, you are telling like, can we always formulate a mathematical equation to compute similarity between two objects?
Yeah.
So the modeling is it's going to be complex, right? How many variables is going to be involved in the modeling? So that's the whole point of why we actually coming to a modeling framework. We are not interested in really what we are actually looking for, but we extract features that are going to be some abstract representation of your original data. So that's something that we call as features. We extract features from your original images, and we are going to work in that feature space. And for your part of your question, yeah, we are going to use this Euclidean distance kind of a loss function at the end of your network to make the final decision whether it is similar or not similar. So did that answer my question? Your question?
Yeah, it is bit clear. Like it is bit clear. I have understood. Like I got a little bit of confused by myself.
Okay. So yeah, feel free to ask more questions. Okay. Just. So yeah, so this is what we were talking about in traditional machine learning approaches. The feature extraction and the final classification are disjoint, so they are not optimized between each other. So what is the problem with that? The problem is that we need to make it more optimized, right? The feature should know what is our final end goal, what is the final end goal of our model. So that is done through the advent of CNN, which resolves the issue by extracting representation of the input data, conditioned on what is our final objective. Here in this case, our final objective is to compare between two feature vectors. So maybe things might appear a little hazy, but as I go on explaining some of the examples, it becomes more clear. So let's define the problem, formally define the problem. So what is our input? Our input, as you have seen from the beginning, we have two input pair of image, a pair of image, and we want to compute whether they are similar or not. And the type of output we are going to be interested will be either a binary label, just to say that 0 correspond to being whether they are same, or 1 correspond to whether they are different. Or maybe we are interested in to know how much similar they are. Might be interested to know to get a single real value that indicates how much your inputs are similar. So that real value could be a distance, or maybe 1 minus distance that will correspond to a measure of similarity. So is there a question here?
So have you covered face recognition as a motivating example?
Face recognition as a motivating example. Yeah, so face recognition will be dealt in the few shot learning, but I can just touch upon that also to give more insight to the problem.
Yeah.
Okay. So I'll redefine the problem with respect to the face recognition task. The input will be input images of two personnels in an organization, and we want to make sure the output of that model should be to make sure whether they are same or the same person or they are the different person. Okay. Or it might be we want to get a measure of how much close the input images are. So we are going to make a lot of decisions based on that the decision of the model, whether they're
Yeah.
similar or not similar.
So if I may add, so why face recognition is a good metric learning problem is because the number of faces keeps changing in the organization or in, let's say, on Facebook or wherever, right? And there's so many people, you cannot define each person as a class. That's too much, too many classes or too dynamic number of classes. So it's better to have some reference photos of each person, and then just do a verification whether this is the query image is the same person or not. Okay, so it is close to one of the database images or not. So that's the metric learning problem. Go ahead.
Yes. So this motivation which has been just given would be the one which we'll be using most often for our few shot learning framework, where we say that we will be answering the question that uh, can we learn from a few set of images? Can we learn the characteristics of the employees? So we are only having a few set of images per employee, but a large number of employees are there. So the kind of question we'll be answering is that the number of classes will be very large, but the number of images per class is going to be very less. Okay, so let's come back and let's see the first solution that's been put forth in CNN framework for metric learning. Uh, it is something called as constructing a Siamese network. So Siamese is a word most of you might be familiar with. Siamese is kind of representing twins or something. So as the name suggests, we are going to use two models which exactly the same weights or exactly the same parameters. And how we are going to use is going to be interesting. Let's say you have this image X1 of an employee and image X2 of another employee. First, we will gonna input this. We'll be using the input will be the image of employee X1, and we are going to get the output as the encoding. We'll get an output from the Siamese network. So let's say I should first tell you a couple of more things to make this more clear. So this could be anything. This could anything be your like your ResNet model, your VG16 model, or any of the deep learning models you have framed. And we want to extract the feature from the inputs. So how do we extract the features? We're going to cut this ResNet model till its first FC layer, the first fully connected layers. And we call that the flattened FC layer to be the feature corresponding to your original image. Is there a question?
No, I was just typing some answer.
Okay. So now the same network with the same parameters will be used again for a second employee, and we expect to have a different encoding, right? Because the input is different. Even though the network is the same, the input is different. The encoding that the network produces will be different. Now we are interested in comparing the two encodings which the network is going to create, f of x1 and f of x2. If your Siamese network is well trained, we expect that f of x1 and f of x2 will be far away placed in that feature space, because x of 1 and x of 2 are different persons. If they were from the two identical person, they were corresponding to the same person, then we expect that this f of x1 and f of x2 to be placed somehow closer in the feature space, right? So this is the idea. And yes, is there?
Hello. Yeah, Nikhil. So I had a doubt here. We are going to only compare the features like hair, skin, and all that, eyes, and all that, right?
No, here we are now. We have started. We have left the traditional machine learning framework, and we are going to extract deep learning based features to
Yes, yes,
compare.
that I got it. Yeah, yeah, yeah. So my doubt is, if see here the backgrounds are different, so
Hmm.
you can say that the images are completely far away. Okay. You take a model where both the backgrounds are same. Of course, it's very unlikely because the faces are different. But if there is some similarities in the face and the background is same, then the model may classify it as wrong, right? Like it may classify both the faces to be the same when they're not.
Uh, are you talking about the background of the image?
Yes. Is that
See,
in consideration or no?
right. So the data set on which we are going to interested would be at least having a strong correlation with this label, saying that they're all going to be faces, and the network is going to learn somehow. We hope that the network is going to learn the facial features. Basically, the background could be different. That's true. But finally, if you're given at least 5 or 6 images of the same person, and you're having a kind of Siamese framework where you're going to compare faces of two different people, we hope that the training would finally induce characteristics that are corresponding to the face and would be able to ignore the background as such. We're not enforcing any constraint as such, but the kind of training the Siamese network involved will be high because we are dealing with pairs of images, right?
Yes.
If there are 100 images, let's say we have 10 employees and we have 10 images per employee, how many pairs you're going to generate? You're going to generate huge number of pairs, right? So
Yes.
the number of training examples and the number of iteration the Siamese will be undergoing will be very high. So we expect that after this, once this training is done, we expect that the network would be uh, able to learn that the facial features are the ones that actually discriminate between these classes. Does that make sense?
Yeah, sure. Thanks.
Okay. Yeah. So we as I told you, this is the same network that is used in for both x1 and x2. Uh, in implementation in the tutorial session, you would be seeing that uh, we don't have to have two separate network with the same parameter, but we will be using the same network twice. That's just an implementation caveat. We'll come to that in the tutorial session. So I hope the whatever I've told you is clear, and I'll move on and how to train the classifiers. We're now going to we have the Siamese network with us, and how basically we are going to train this network. We will get this f of x1 and f of x2 corresponding to, or f of xi and f of xj corresponding to xi and xj, and we know that we can create a data loader which can have the labels 0 and 1, 0 corresponding if they are similar, or 1 corresponding if they are different, right? So once we create a data loader, let me explain a little bit more clearly. So, as I believe you have learned about what data loaders or how to create the data set. So this is a kind of data loader which we are creating for this Siamese network. We'll have input XA and XB. If they are same, we'll be giving them the label 0. And if they are different, we will going to be giving the labels as 1. So this is basically the problem. So the input will be two inputs, and the output will be a label corresponding to whether they are similar or not similar. And this output label is going to be used in the training while we are going to train this binary classifier. So how did we make this binary classifier is a question, right? So we have features extracted from the two Siamese network. We are gonna have concatenate this together and add some FC layers, and we can finally make to a single scalar value which we can use to compare and make an end-to-end training. Okay, is there a question?
Basically, in the data set, we will have all the possible combination of xis and xjs.
All
Where
the
if they are from
possibly,
the same
yeah.
person, then it will be having a label 1, or else it will be 0, right?
Yes. So all the possible combination may not be always possible, because if the data set is too large, how much of combination will be there? There'll be huge number of combinations, right?
Yeah, the idea is that, but I mean, if more combinations are there, that is useful for the model, right? To
That is, yeah, exactly. That is useful for the network, but it may not be able to see the entire pairs. But most often we'll come to that. Most often we actually randomly select the pairs and try to establish the Siamese framework, and it's having its own drawbacks.
so basically, the random formation of pairs still happens, but it is not in the wholesome sense. Like it is not for entire combinations, but probably a portion of it, right? In simple terms.
Yeah, randomly for a portion of it, that basically, and that's one of the drawbacks why Siamese is not effective. And we'll come to later on to triplet networks, where we have a strategic sampling, so that we make sure that the network is going to be good.
Sure. Thank you.
Okay. So is there another question? Okay.
No, I'm just typing some answers. Go.
Okay. Yeah. So that was how Siamese could be designed with as a binary classification. Now we'll look at how can we do the same thing based on the distance loss, or the distance metric we have defined. The same framework again. We have x1 and x2, the two patches fed into the Siamese, fed into two CNN that share the same weights, and we are going to get two encodings, d of x1 and d of x2. And somehow we are now what we are going to do is that we'll be interested in a distance-based loss function. Let's say that the very intuition would be that the same patches, if x1 and x2 are from the same object, their d of x1 and d of x2 should be closer to each other, and if they are different, d of x1 and d of x2 should be large, so that x1, the features will be placed at a very far distance in the feature space. Let's see how we actually implement that mathematically. So we'll come to what is to some of the most commonly used loss functions in Siamese network. Just for clarity again, I've posted this. So here images of two airplanes are compared. They are given to Siamese network that share the same weight W, and we'll be finally getting a distance dW, and we want, our objective would be to make this small. However, if it is between an aeroplane and a car, our final objective will be to make it large, right? So how do we quantify that? And the final loss function would be the sum of the loss of positive pairs plus the sum of the loss of the negative pairs. So we are going to deal in this mini batch scenario where you will have to deal with both these kind of images, the similar images and dissimilar images. So this is typically called as the contrastive loss function, where our aim would be again iterating, if they are the positive pairs, that is they are the same, then we should minimize their distance, and if they are negative pairs, then we are interested in maximizing their distance, right? But maximizing distance is something which we are unfamiliar of. We will be interested in the minimizing objective itself. So how do we turn this maximizing objective to minimizing objective? We can reframe this maximizing objective as minimizing from some infinity. Although we cannot model infinity, we say that there is some infinity, and we put negative of the distance between x1 and x2. So if I'm minimizing this x1, x2 now, the whole objective becomes maximizing dW of x1, x2. The whole objective becomes just to minimize the this quantity minus dW of x1, x2 plus infinity. So we can't, as I told you, we can't model infinity. What we'll do is that we replace infinity with a margin. Let's say we define a margin based on our problem, and we'll replace this infinity with that margin. Then the objective will be modified as minimizing m minus dW of x1, x2. Is there any question at this point?
I mean, in order to maximize the distance, why can't we just take the negative of dw x1 comma x2? Why do we need to add the positive
Yeah,
term?
so finally, as I told you this is the final loss function we are expecting, right? Some of the loss pairs are, because we are going to do that in the batch framework. Now we need a similar scales for both the pairs. If we are going to take negative, we want to make sure that the loss function will still remain and will correspond to our distance framework. So maybe why not can we take 1 by of this distance? That's also possible, right? So the basic idea is that we want to make sure that we have a margin. We will have a margin set, and we are going to work with this distance idea itself, where we say that for dissimilar samples, we want to make sure that the samples will always be placed beyond a margin M. So this intuition has to come in, right?
Okay, yeah. Now it makes sense. Yes.
So this
But
intuition
another way would also be, instead of learning the difference between them, like the Euclidean norm, right? Instead of that, if we simply use a softmax, right, it would do the job the same thing.
Yeah, exactly. So that's the point which we were talking about in rather than using a Euclidean distance, why don't we convert this to combine the features together and convert this to a single vector and can use a sigmoid or a softmax function, right? That's also possible. So there are different implementation. Since we are now discussing about contrastive loss function, where we are interpreting that our final intuition would be to place the encodings, the similar pairs to have less distance and the dissimilar to have maximum distance. This is the idea we are interested right now. Okay, so I'll come back to that. So as I told you, we are interested in having a margin between positive and negative samples, and if the inputs are x1 and x2 are similar objects, we like to place them as close as possible. So in a in a mathematical sense, we want to actually make them a single point in that feature space, right? We are minimizing the Euclidean distance between them. We want to actually make them a single point. And for as far as the negative pairs are concerned, we want to maximize the distance so that we want to place them as far as possible. And to define how much as far as possible, we define something called as a margin, where we say that we'll be happy to set the loss as 0 if these points are placed beyond that margin. So that's why this loss function is modified to something which you are already familiar in your SVM, support vector machine lectures. You have already come across this loss function, where we say that if the distance for dissimilar pairs, if it is greater than dw, let's set the loss to 0. We are happy with that. Okay. So the final contrastive loss function, which we will define is a combination of both the terms. If your samples are dissimilar, we'll be interested in maximizing the distance, and if your samples are similar, we'll be interested in minimizing the distance. I think there's a confusion here, because earlier I defined 0 to be similar 0 to be similar samples and 1 to be dissimilar samples. So this loss function basically is actually doing it. If y is equal to 0, only this term remains. And if y is equal to 1, this term will remain. So y is equal to 1 will correspond to minimizing the distance, and y is equal to 0 will correspond to maximizing distance. Is there a confusion?
No, we are just having a chat. Go ahead.
Okay. So this is the final contrastive loss function. Yes.
So here, shouldn't it mean if y is equal to 1, then the images are similar?
Yeah. So I think that I've
It's
defined
the reverse, right?
I think I've defined that differently here. So maybe this should actually have to be 1 minus y and y. So
yeah, that would do it.
that would work, right? So I think
Yeah, that was.
sorry about that. Is that confusion clear?
Yes.
Okay. Okay. So this is the final contrastive loss function which we are talking about. Now let's examine this. We'll examine this contrastive loss function in detail. Before that, I just want to mention some of the another popular Siamese loss function, where the idea is to work with angles of the feature vectors. Let's say if x1 and x2 are two features extracted from different images, then we have the intuition that if this x1 and x2 are orthogonal, we say that they are different, right? That the angle between them is somehow 90 degrees. Then we say that they are different. And if x1 and x2 are in the same direction, we say that they are corresponding to some similar entities. So the same concept is used to define something called as a cosine loss function, where we are interested in knowing what is the cosine of the angle between x1 and x2. And depending upon that, so instead of our Euclidean distance, we'll be using the cosine of angle to define the distance metric. Okay, so this is just to mention that there are papers which have been using cosine loss functions also in Siamese network framework. Now we'll basically analyze a problem with Siamese network with respect to the contrastive loss function. If you examine this contrastive loss function, you basically say that for each input image, we are actually having only one of the terms in this loss function being optimized. Either it's a positive pair or either it's a negative pair. Only one of the pair will be optimized. It's not giving any global context. So I'll explain that again. If I am having x1 and x2, which are similar, then I know that from my contrastive loss function, I should minimize the distance. That is clear. Now I'm having x3 and x4, which are different. I know from my contrastive loss function, I should increase the distance. But we're not doing this together, right? Somehow the network is losing the idea that x3 and x4 were different, but they are not. The backpropagation or the gradient update was not done in this simultaneously by doing x1 and x2. Am I audible?
Yes, you are audible.
Yeah. So yeah, okay. So x1 and x2. So there's some kind of a toggling that happens in this contrastive loss function that tends to lose the whole information, that tends to hide the whole information about in a global context. If I hope that will make sense, because we somehow for hard problems, the network will mostly is going to settle for median distance, because the network is not aware of the global context in which it should minimize or maximize. So did that point make sense to everyone? Yes.
Yeah, Nikhil. Could you go to the slide where, the initial slide where you had two images and you explained CMS, where it started CMS?
Okay. This one?
Yeah, this one. Yeah. So here, see, this the final fully connected layer which is there.
Yes.
It is going to have certain number of values, right?
Yes.
And so it is going to compare each value, right? The first value of the first vector with respect to the first value of the second vector. That is how it's going to go, right?
Yes.
And there we apply the distance metric, and based on that we do the loss function. Then if we are doing it point wise, what is the point in knowing if, for suppose, see, with respect to the first 2 points, I get that they are almost similar. Okay. I will optimize that. But
yeah, let me clarify that again. The features, what you're obtaining here will be a vector, right? Some vector of values.
Yes.
Let's say this is 128 dimensional feature. So we are going to examine this feature is going to be a point in that 128 dimensional feature space, right? So let's say this is if it's just a two-dimensional feature vector 1 2, we know that it's going to be somewhere in two-dimensional space. This is just a point, right?
Yes.
So similarly, if it's a 128 dimensional feature space, this vector or this feature we are going to get is going to be a point in that feature space,
Yes.
right?
Yes.
And we are going to we have defined through our metric that the distance that correspond to that feature space and things like that, right? Does that make sense now?
Yes.
So define L2 distance. So all these things are with respect to that feature space.
Yeah, I got it.
Okay. Okay.
Actually, what you told is that when we should concatenate them, right? And what I was saying is that we don't do anything. We just pass them through, and we just simply compare their basically the end vectors, the last vectors, and if they are like the cosine similarity between them is above 0.5, it means that they are similar. If it is less than 0.5, then they are different, right? No, I mean the opposite.
So
I
you're
think,
telling
yes,
like we can
the same order, yeah.
Can we define a threshold from which we
Yeah,
say
yeah,
that?
and basically just compare these like as vectors, just compare the vectors simply by using cosine laws, and by the threshold decide okay to which whether they are same or whether they are not same, and then learn the whole representations like that.
Yeah, so that's also another possibility. So learning a threshold and learning this thing is also possible. But the drawback of the entire scheme where we are just assigning a 0 and 1, we do not get a how much, or we cannot quantify how much similar or dissimilar they are, right?
Okay, yeah, yeah.
We are just hard thresholding. We have some threshold and we say that it's similar or not similar. So that's the primary reason why when we are going for this distance based loss function, we say that let's get a real valued number that would give an idea of how much similar they are. Does that clear your
Yeah,
doubt?
but yeah, that's correct. But eventually, what is supposed to happen? I mean, if even like if we kind of train it on this basis, right? You know, the label is 1 and the other label is 0, but still, if we will do the dot product between the last ones in order to get the cosine similarity, they'll still be somewhere between 0 and 1, right?
Yeah,
For
but that's a real
during the
value.
test time. Yeah, so
That's
that is
going to be a real
definitely
value
not
number.
going to be an absolute number. That will also going to be some like a quantitative metric only, right?
Come to that. So you're saying that here we'll compute the cosine similarity between x1 and x2.
Yeah, yeah.
We are going to get a real value number between 0 and 1.
Yeah.
And that's going to be a real valued number, right? We are not thresholding it anywhere.
Yeah, we don't threshold it, but in a general threshold, like sense of thresholding, we simply put like a number like 0.5, or depending upon like, like changing things by taking some values from ROC curve or something like that.
Right. So during the training time, we are not thresholding. That's the point.
Yeah, during the training time, we are not thresholding. After that, not like how generally any classifier
you're correct.
would do the prediction. Yeah, then
You're correct. You're correct. Yeah, but during the training time, we are not thresholding. But the earlier when we were using that Siamese as a binary classifier, we were thresholding in the classifier itself.
Okay. Yeah.
Right.
Yeah.
So yeah, so let's just discuss what I've the drawback of the Siamese network. So drawback of Siamese network, yeah. So Siamese is just a the contrastive loss function we are using has updates differently for each inputs. So it's not giving a reference from which how much it should maximize or how much it should minimize. Maybe for the first input, it's only taking this part of the loss function. For the second input, it's taking only this part of the loss function, but it's not providing that information about or it's not providing any reference from which it should maximize or minimize. Is my point making sense? So the Siamese is losing the global context from which in it should work. So let's see what is the remedy for that. Then maybe we can come back to this point to make it more sense. If we are having something like a triplets, let's say we have instead of a pair of images, let's say we have 3 images taken together, and we call the first image as anchor, the second image as a positive, and third image as negative. And the intuitive idea would be to so let me define these terms. The positive refers to the image which is same as the anchor or the similar kind as the anchor. Negative would be the different than the anchor. So as you can see, these are the same persons, and this is a different person. The positive will be the same as the anchor, and negative will be a different person, different than the anchor. So our intuitive idea here would be that in a single step, if we are given 3 images at a time, we can simultaneously maximize the distance between anchor and negative, and minimize the distance between anchor and positive. So in one iteration itself, we are given the idea of optimizing it together. When compared to your Siamese loss function, this was not happening. We were doing everything disjointly, right? We are only having pairs of x1 and x2, but we were doing the update disjointly. Now, when we come to a triplet loss function, we are given more information, and each of our gradient updates, since we are having triplets and we are going to deal with this triplet based loss function, each of our update is going to give us more sense.
So as compared to the earlier loss function that we had, we just will remove the y term that we had in those, and it will actually be constantly optimizing for both the things, like making the similar ones closer and pushing the dissimilar ones further, right?
I think he stopped. Hello.
Got it. Yeah. We'll wait. No problem. Let him reconnect.
Yes.
Yeah, well, maybe ask him to reboot his modem. Usually, that is the issue.
Amit sir?
Oh, we lost Nikhil for a bit, right?
Yeah. Am I audible now?
Yeah. Audible.
Did
Yeah.
I? So, what did I stop in between? Because I was feeling that I was online. I was explaining. Till what point was I audible?
I think the moment till I asked the question, I mean, if you remember, if like that I asked.
Okay.
I mean,
Okay.
the thing that the y part gets removed from our earlier equation, that is what is going to happen in the case of triplet loss, right?
Yeah, triplet. So, did the explanation of triplet loss was recorded?
I don't think so. I don't know.
Okay.
I mean, I don't think so. It was done.
No.
Okay. Yeah, let me just explain that again. We are going for a triplet loss function because in triplet loss function, we have something
Nikhil,
called
your screen is not shared.
screen not shared. Okay.
Are you sharing your screen, Nikhil?
Yes. Now is it shared?
Yeah.
Okay.
Your entire yeah. Now it's shared. Yes.
Nikhil, I
Okay.
had a doubt.
Yes.
Yeah, so to the Siamese network, uh, is it like you'll be passing many images while training, uh, and every time you pass, normally for a model, like if you're doing, semantic segmentation or whatever, all those things, we pass one image, but here we are going to pass a set of images, like 2 images,
Yeah, we're going to pass a pair of images.
pair of images, right? And
Yes.
that we pass many pairs to the model.
Yes.
Is it frozen again or?
Okay. Okay. Hello.
Yeah, yeah, yeah.
Yeah. So what was the question? Question was completed.
Yeah, yeah. That was it.
Okay.
Sorry. Yeah.
So here we are examining the drawback of Siamese network, that it's not giving you the global context. If you see the loss function, it was just toggling in between similar and different pairs, right? And it was not giving the global context. But when it comes to triplet loss function, what is happening is that we have something called as an anchor image and a positive and a negative image, where anchor and positive correspond to the same subjects, and negative correspond to negative and anchor correspond to a different subject. So here in one go, we can optimize such that the anchor and the distance between anchor and positive should be minimized, and the distance between anchor and negative should be maximized. In one go, we can make an optimization step like that. Then it will give you a more uh, relative reference from which the optimization can be more effective. Does that make sense? Compared to your pairs in Siamese network.
Yes, yes, got it.
Right? So that's why we need something called as a triplet network that comes into our the whole metric learning framework. That is more advantageous because it's preserving that reference image from which then positive and negative could be optimized. Okay. So
Nikhil, can this be used for videos as well? If we extract the frames and skip few frames, can we use this for videos as well?
videos for what is the final objective? So similarity learning, yeah, of course. If you're dealing with a question, whether it's a binary, whether there is a binary answer, whether they are, whether it's yes or no question, yes, you can make and model that as a metric learning question.
Okay. Even for videos as well.
Yeah. So the use case should be such that we are answering the question whether they are similar or not similar.
Okay, got it.
Right?
Yes.
Okay. Yeah. So at this point, I would like to switch to Ravinder. Ravinder, are you there?
Yeah, Nikhil, I'm here.
Yeah. So Ravinder, I think you can take over from here.
Okay. So do I need to share my screen or yours?
Yeah, you can share. I'll stop sharing my screen.
Okay.
Thank you, Nikhil.
Oh, okay. So hopefully Nikhil has already communicated that why we need this type of strategies because we wanted to do all things in a single shot. So let me move ahead with this philosophy. So basically what we need is we need triplets. So when we are talking about triplets, there will be one anchor, then the other one is positive. The positive is that is the similar match with the anchor, and the other stuff is negative, that is not matching with the anchor. So suppose here A and B, so A is anchor, so B is positive case, and B is matching with A, and C is something that is not matching with A. So every time when we are going to train our network, we are going to have the cases in case of triplet. So in order to do that, we need a triplet loss function. So what does this triplet, so why we need it? So we need it to we need it so that we bring the embedding that are we need it so that we can create a large distance between the embedding that are not similar and the small distance between the embedding that are similar. So if you see this, this is something that this is that anchor, and this is for positive case, and we will try to minimize this, and also we are trying to maximize this. So we are trying to maximize the dissimilarity distance and minimize the similarity distance. So here the another thing is alpha. So why we are taking that alpha? So we need to include it because otherwise what will happen is if we remove that alpha, so there will be two scenario that we can easily think about. One is that what if the system generate all the embeddings to zero? So this equation will be easily satisfied if alpha is not there. So we need to put some margin in order to move away from this trivial solution. The other thing is that what if our system generate same embedding for each and every image? So also to cope with that, we need some margin so that system won't do that. So our loss function in this case will be this. In this, what we are doing is we are minimizing this distance and we are maximizing this distance. Hope this is clear to everyone. Am I?
Yes, yes, you're audible and it's fine. Please go ahead.
Sir, sir, can you just maximize your screen by pressing function F11?
Okay.
Yeah, full
There is a
screen.
different functionality. I mean,
Maybe
I'm on Linux
you can
F8.
right click on the taskbar or someplace and make it full screen.
So I guess this is some PDF. So I don't know how to maximize. Can
No, in the
anyone help me?
browser itself, you can
Yeah.
make it full.
Okay. So okay, how to do that?
I think it's functional F11. It doesn't work.
F11. Okay, it's okay.
Yeah,
So it's
good, thanks.
different functionality. So we, as we already know that we need a triplet. So, but why? So in order to select that triplet, we need a strategy because we cannot randomly select the triplet. So what happen if we randomly select the triplet instead of we are following some strategy? So let's discuss about that case that if we are randomly selecting. So if we are randomly selecting, what happen is we might select a case that is easy to distinguishable. So if I am selecting something is positive and that is very near to it, and the negative case is very far away, then our system will automatically detect that. So and in a way the network won't learn anything. So we need to provide certain examples that are very hard. So in case of positive, we usually say that if something is similar, so let me explain with this diagram. So our strategy will be, so what I was telling is, if I will take the easy negative case, so if this is my anchor and this is my positive, so if I am taking the positive here and the other and the negative case lie here, then it will be easy for system to differentiate because the distance in case of negative is already very large and in distance in case of positive is very small. So so if we take example, if we are randomly selecting and taking example in this way, then system won't learn much. So there are possibilities that system won't learn much, and we end up with not a good solution. So we need to define a strategy where our so we need to define a strategy so that we select the examples that are hard to distinguish, so that system will learn something good. So usually what we do is uh, what is hard. So let me explain what is hard negative. Hard negative is something whose distance is kind of similar to the positive distance and lie within the boundary of this. And the same similar the hard positive will be something that is that is lying with this boundary, and anything that is at a very far distance is easy negative, and anything that is very closest is easy positive, because system will easily detect it, but we need to train it for the hardest case. So our philosophy will be to select the cases where we take the hard positive and hard negative examples. So usually what we do is, instead of picking the hardest positive, we use all the anchor positive pair in a batches while selecting the hard negative. So if you go through that FaceNet paper, what they did is they select the all the positive. So they select the positive cases despite the hard positive or something, and then they go for the semi hard negative stuff, because they observed that if we go for a hardest negative, then that might lead to a bad local minima at a very early stage in the training, and it might result in a collapse of the model. So in order to mitigate this, we can select hard negative. We can say that semi hard negative, as they are still away from the positive, but still as hard as their scared distance is close to the anchor positive. So we need to select those hard negative that are lying within this margin. Instead of selecting the very hard negative, we need to select the semi hard negative. So this will be strategy in selecting the triplet. So there are basically two strategy. One is offline and another is online. uh, Online triplet mining, so you can go and explore those, but just for an idea, what we do in offline triplet is that uh, assume that there are 10 images. So for case of offline triplet, we select something with, so for the 10 images we select the 30 embeddings. We are just multiplying the images with the triplets number, with the numbers of the images in the triplets. So generally the practice is that we use the offline triplet mining, because it is in a way we don't need to store the things, and the numbers of embedding generating will be less, because in case of online triplet mining, if we are having 10 images, then we are somehow selecting only the 10 embedding. So in online triplet mining, the numbers of embedding will be equal to the number of images that we are going to feed. So the question is, so hope that triplet stuff is clear. Let me know in case you guys are having any question. I'm not hearing any voice. Should I
Yes,
move on?
yes, it's clear. Please go ahead. Yeah, please go ahead.
So the one strategy is that few shot learning. You all might have heard about it. So okay, someone raised the hand.
Yeah, Abhijit. Oh, sorry.
Yeah, please ask questions.
Yeah, could you please go to the previous slide once?
Okay, this one.
Yeah. So, see, sorry, no. I mean, about triplet. See, so to the model, we have to handpick the triplets and give it, or already online there is someone who has done that for us.
So there are two strategies that has been developed and people are using it. One is offline, but usually offline is discarded in a favor of online, because offline required lots of computation because the number of embeddings are large as compared to online. So there are basically two flavor for online triplets mining. The one is that they are selecting somehow the hardest examples, and the other is that they are keeping focus on the semi hard negative and the positive examples. So you can explore those. There are in detail, and there are kind of different algorithm for that, how they are selecting it.
Okay, so again, like to create this triplet, we have to, compare distances again, right?
Exactly, exactly.
We have to create a separate model. Okay, I'll read about that and get back to you if I have it. Yeah, thank you.
So
Hello.
why we need few short learning? So just to give an idea and set an example, we all know that humans are very good at learning with a very small number of examples, and there are the things that we see once, and apart from remembering those only for very long duration, we also have an ability to identify those things among hundreds of other things. So one might learn how to drive a manual car and be able to drive any automatic car, the minimum amount of shift in the learning, because we know the fundamentals and we know how to do that stuff. So that is learning with the minimum samples, because once we have learned how to drive manual, we can easily generalize it. So this comes with the minimum sample and minimum generalizability. So in few short learning, we want this to happen. So we are crazy about how we can map human intelligence with that, how we can map that computer intelligence with human intelligence. So people develop this philosophy and their research going on. So one of the things that we are going to discuss today is how we can do that face recognitions with one short learning. So if I ask you a question, so till now you have gone through all Siamese network and other, you might have gone through other networks also. How would you solve that face recognition problem? Basically, any, I mean, I need your views so that I can might have an something like I didn't think about. So any idea from the audience?
Meaning which approach is the best approach, or
Uh, Not the best, but whatever coming in your mind. I mean, if someone give you an example, okay, this can be solved with face recognition, and uh, from your toolbox, how will you gonna do that? I mean, what are the challenges that you think that can be arrive, or what are the things that you think that you are very confident about, and then you can do it very easily? I mean, what will be you general approach for that? So that I'm
How
making a
about
point. Yeah.
take the eyes as the feature to get the pixels for
Okay.
the feature recognition and do it like that, like something unique instead of going with the like identify the eyes first and then pixelate that as the feature and then
Okay.
go for.
That's good. Uh, any other example apart from this? Okay.
We can
Let
do the
me.
triplet loss function. I mean, if we can mine the semi-hard examples, then we can simply use a triplet loss, right?
Yeah. So that's the fundamentals of the one-shot learning. So that will come in the picture. Okay. So let me frame a story. So we all know that deep learning requires lots of data to train. And what if we don't have that much of data? So what's your normal strategies? Okay, give me the data. I will do whatever you want. So if we want that, okay, there is a single image. So the general philosophy is that, okay, boss, I need 10 or 100 of images for a person so that my model will learn something good. So these are the scenarios that I am talking about. If we don't have that one short learning or few short learning methodology into pictures. So, and we also, so assume that you are building a face recognition system for your organizations or college or say any XYZ group. So the task is given an image, identify the person in image, right? So how would you do that? Well, you might.
just one clarification. Are we talking about only images here, or does this apply to video as well?
This can apply to video as well, but to be very frank, I haven't gone through that stuff. But yeah, video is just a frame, so we can select the frame we want to investigate, and we can easily apply. I mean, that's my understanding.
Okay.
I have a question.
Yeah, please go.
You have during the training you have left the very hard very hard problems, like those which are unable to distinguish hard positive or hard negative, but you have gone with semi hard. Why is that?
So in case of selecting, so it has been observed that if we are going for hardest negative things, so let me talk about the hardest negative things because that is the case that has been observed. So if we select for the hardest negative, then that might lead to bad local minima at a very early stage in the training, and this might result in the collapse of the model. So that's why in order to avoid that risk, you can go for it, but you need to vigilant about what is happening.
So like
Yeah, another reason would be that the hearts triplets will correspond to noises sometimes. So we don't want to
Yeah.
train your network on outliers, right?
Right.
okay, thank you.
Okay, so we were discussing a fictitious scenario where we were trying to build a model. So, okay, so where were we? So how would you build that model? So well, you might say that let's train a connet and apply a softnet function in the end to identify the person in the image. But the main issue is with that problem is your softness function is limited by the numbers of people in the training example. So say if you have 100 people in the training set, then you are training it to identify the probability of image belonging to each one of them. In a way, this can be done. But what if the new people join the organizations or the institutions you are building your stuff? Do we need to retrain our entire model to adjust it for the upcoming or the number of people? So this, I guess, this seems like not a good solution at all. So what's the alternative? So the alternative is to why not build a function that can be used to match the image in the database? Why not have a function that is able to adjust the new changes in the image and still able to recognize the image? So we all know about this function. Let's call this function the distance measuring matrix, right? So what we can do is we can have some distance. We can calculate the distance between two images. And we can say if distance is less than some threshold, so it's the same person. And if the distance is greater than some threshold, then it's the different person, right? So, but we need to select what the threshold will be. So we need to train for it. So, and that distance might be very large if that person doesn't belong to that in the database. So how will we do that? What we do in order to build that stuff with a fewer number of example and to increase its generalizability is that uh, this is what uh, they have proposed in their paper. So what they did is here is any deep learning architecture, might be CNN, for instance. And whatever we are, so what we are doing is we are passing an image through this architecture, and then we do that L2 normalizations, and then we create an embedding. So this is a, say in their paper, they are using 128D vector. So we can do that for each and every image. So once we train it, we need to keep this architecture and all the parameter constants when we are passing our images. So after that, so once we pass the image that we want to compare, we will have embedding, and on those embedding, we will apply some distance metrics and we calculate, and we will use triplet loss to train our models. So any questions so far?
What is embedding? Can you please explain a bit?
Okay, so you can see the embedding is, if I scroll up for that thing. So if you just remove this softmax, so this is the part that you are getting before softmax, but before that you need to apply some normalizations, see L2 normalization, and after applying that L2 normalization, whatever you are getting, maybe the n dimensional vector, that is your embedding. Is
Okay.
this clear?
Okay,
Okay,
I will just
we are
go through
working
it.
with.
Sir, so basically we create an embedding for each image, and we directly compare with the anchor, and so that's how we predict it's a positive or negative. Like don't save thousand of image in the database, instead of saving just one and compare with each and.
Exactly. Correct. Yeah, to the point.
Thank you, sir.
So if we are going to, if we are going to differentiate these two images, we need to identify whether these are similar or not. What we'll do is we will pass these two images into our train network, and we will get embedding, and then we will apply the function that we have already trained, and that will tell us. So let me go through that also. Okay, so we have already discussed that triplet loss, that we need to minimize this and we need to maximize this. So our minimization objective will be this. So we need to overall minimize this function. So anything about that, because we are moving for a prototypical network. We are done with that. Should I silence
Yes,
it
yes,
or?
please go ahead. Please go ahead.
So the same strategy can be applied using the prototypical network. So in prototypical network, what we are doing is, so assume that, so this will be the case of 1 2 3 4 5. So this will be the case of what I call that 5 short 3 way, because three are the numbers of the classes and 5 will be the numbers of example per classes. So what we do in prototypical network is we calculate the centroid. We calculate the centroid of example of each classes. So we will calculate the centroid of this, we calculate the centroid of this, and we calculate the centroid of this. So once we have centroid of this, so these are the centroid. So what we are doing is we are passing each image, we are generating its embedding. So there are 1 2 3 4 5 embedding, and we are taking the centroid of those embeddings. So there will be one centroid here, one centroid here, one centroid here. So there will be 3 centroid, and now we will have new example. So it's like k-mean clustering that we did previously. So if the new observation comes, so based on these distances, we calculate the distance. So once we calculate the distance, what we do is we take a negative, so that we can convert distance into the similarity measure. So the largest the number, the higher the chances of belongingness. So what we do is we take the negative of that distance and we apply the softmax function, and the end result will give the class which the observations the upcoming image will belongs to. So this is how we are calculating the centroid. So this is just a representation. So let me share another, I guess that is in another file. Okay, just hold for a few minutes. Let me share it. So is my screen visible? Hope you guys are able to see it.
Yes, yes, it's visible.
Okay, so the if you see this example, so the objective is, so how we achieve this. So once we calculate the distance of how the steps So how the steps are, we calculate the centroid, and after centroid the new images. So once the new image come, we calculate the distance, we take the negative, and after that we apply the sigmoid function, and we calculate the probability of belonging class. So this is the objective function that we normally use. So I pruned that out for better explanations. So the function is somewhat complicated in the paper. So I pruned that out for just explanations. So this is our minimization objective. So what we are doing here, so what this function is doing is basically okay, so this is just a negative log probability that we want to minimize. So if I say this y is equal to k is the class that we are going to assign, and here X is our image. So we are giving an image and we are assigning it. So I am just breaking it down. So how, so this is just a negative log probability, and I am just breaking it down. So you can break it down in a way. So that here we are calculating the distance between the centroid. So CK is for the centroid, and that image, the distance between that image, and we are just summing up all the you can say, so this is a kind of sigmoid of all the things. So we are taking sigmoids of, so we are calculating the distance, and we are taking the sigmoids of all the distances, and this will give the probability. And if we will decode this, and if we take a log of this, then the end result will be this equation. So this will be our negative log probability function that we want to minimize. So this is for prototypical network and one-shot learning. Any questions so far? I guess we are done with it. I don't have any. Thank you, slide. Sorry for that. So any questions so far? Hopefully things are clear.
So this has nothing to do with when the data set is less.
This has to do with I mean these are the techniques that people use when your data set is less, because this is an example of few shot learning. So basically it is falling under that meta learning stuff. So I skip that part.
Yeah. Because I didn't have a question. I just wanted to know your thoughts about one thing. So in one of my project, or in one of the papers that we are trying to develop, we have this problem. So we had two problems. First was we were trying to do gesture prediction, recognition, and prediction. So we tried to solve that problem by going for depth-based segmentation. And once that was solved, now we have this data set problem where we are generating our gesture data set, but we have very few short videos. So can we do can we use something like this for dynamic gesture based recognition scenario where we have very less data set, like very less videos?
Yeah, I guess as from my experience, you can try out that, and there are also stuff not for, so this is for metrics learning. So there are other steps also where we can combine the combinations of metrics learning and the meta learning. And so there are the algorithm you can check out. So there is couples of algorithm that are coming out as a combinations of meta learning and then that metrics learning. So there is you might be familiar with that data augmentation. So combinations of these three strategies people normally use in that case where the numbers of cases are less. I mean, the data is very less. So you can try out those approaches. And these are the things that are, I guess, that are frequently in use where the numbers of data points are basically less as compared to the last. And we are just using the transfer mix combinations of transfer learning and plus these things in order to in order to drive our objective. So you can check out also that stuff. So meta learning is the things. So I guess that is picking up very fast. And I mean there are 3 to 4 years has been passed, and people are using it. In Google has developed so many things over that. So you can try out that will be definitely beneficial. I mean these are my I'm not an kind of that much of expert in that area,
Got
but
it.
yeah, these are my thoughts in that.
I just wanted to know your thoughts on it because for images I have seen, but our work was related to dynamic gesture. So yeah, thank you for your thought.
Yeah. Should we wrap up or any question? Can I assume silence is a no question?
And also one more last question. There should be some threshold also, right? Like less data, how less there should be some threshold beyond which you can't that data set becomes unusable. Anything like
So
that?
in case of, if you see this recent example, one shot learning, we are just comparing two examples.
Mm-hmm.
So if you are having that network ready, so you are okay with even two images also.
Oh, okay. Okay. So two images in the sense, do you use only those two, or do you generate some synthetic data, or do you use only those two? Something like
Two images, it's up to the case. I guess you can generate the data if you feel like, but I guess it's a basically direct comparisons between the two things. So in case of one shot learning, you are comparing whether the pixels belongs to that person or not. So you can direct. I mean, there are ways if you want. So as I mentioned earlier, if you want the combination, then you can go for that combinations also. There is no restrictions in terms of that thing.
Okay. And also, there are lots of these days, lots of mask or no mask videos that I'm seeing. So, is there any segmentation done in that case, or how do they detect that?
Okay, masking. I'm not much familiar with that thing, so I mean, I cannot give that answer.
Yeah, because we faced a lot of issues. We first tried with normal videos. Let's say 10 people trying to replicate the same gesture, and then we tried to do recognize the gesture in real time. The accuracy was very low. So then we went for depth based segmentation, where we went with Kinect camera and we got RGB depth image, and then the accuracy improved. So I was just wondering how do they do it in real time. So I had a question like that without using any what segmentation approach they would use. Just had a
Okay.
question.
Sorry to
Yeah.
say, but I'm not an expert in that field, so
No
I
problem. No
cannot tell you
problem.
much.
Yeah. Thank you.
No issue. So, calling it a wrap, I guess we are done with questions, right?
Yeah. Thank you very much, Ravinder. Thank you for your
You're
time.
welcome. Thank you, everyone. Thank you
Yeah,
for
in
listening.
chat there is one question.
Okay, so yeah, please tell me.
In
I
chat there
am
is one question.
just not familiar with the interface.
So I will just read it out. The question
Yeah,
is,
please do it.
the face embedding is the embedding that you explained in. So maybe you just read it. I don't know. It is clear.
Okay. Wait. How to get there? Okay, chat. Got it. Where it is? Okay, I was getting there. Sorry for that speed. This was for me. Okay, this was for some. Okay, this was for me. Okay. The face embedding is the embedding that you explain in and to image. So Satyajit, can you please rewrite it? Entire is it entire image or different?
Satyajit, just unmute
Yeah.
yourself and ask the question.
Yeah, sir. Actually, I was asking the embeddings that we have generated, right? That vectors from the entire image. So I used to read a lot that there are some face embeddings, the like key points in the face. So are
Okay.
those embeddings are different from these embeddings, or both are same, something like that?
So key points, you are mentioning that we are only extracting the features from that image and then we are doing the embedding, right?
Yes. Only the some like 16-point features where we are recognizing only the eye points
So
or a nose or lips or something like that.
So this particular network, because it didn't go into that much of depth how they did it, but yeah, they only mentioned that they use different deep learning architectures and different layers, and I'm not aware about what those layer are doing in their network. But yeah, you can create a layer to extract the feature and then further move on with this architecture. I guess that will also generate the embedding, but that will be related with your particular case only, I guess. So in that case, so whatever you do, you can play with different stuff, and whatever you do, you need to keep all the things, all the parameters and the complete architecture same for each and every image. And I'm hopeful that that will work for your case also.
Okay, okay. So I think internally in deep this architecture only, they will be learning that key points.
Exactly. Yeah, it's
Yeah.
up to your case. I mean, it's up to one's case. So you can try out any architecture, try out any strategy. So what matters is that in the end, if you are following this, then you can do that L2 node and then generate the embed. I guess these from L2 normalizations, the process basically starts. So this is how I am considering this.
Okay, okay.
So these are my thoughts. You can explore it by reading the paper also.
Yes, sir. So I got it. So in the database, we have to, so the entire, what I understood is in the database, you have to store the images of the different, I mean, the people, and our model is actually taking that as a reference, frame of reference, and we are comparing each and every faces.
Right.
That, okay.
Right, exactly.
Yeah, that, yeah. Thank you, sir.
Welcome.
So embedding are the features based on which we are comparing to images.
So features, so it's a results of combinations of different features that we have generated, and in the end we are generating a vector. So you can say that it's a results of the features. So you might
Okay,
embedding might represent certain feature also.
okay, okay, like some parameters upon which value we will judge whether two images are similar or not.
Right.
Okay, thank you.
So anyone else have any question? Okay, where is the chat box? Can you please explain again? So Sankalp, do I need to re-explain it? You want a reiteration? Things are clear to you. Can you please? Okay, I'm assuming that you want a re-explanation. Okay, no issue. So so in prototypical network, what we are doing is we are creating the embedding of these 5 things. So we are assuming that there are 3 classes, and each class contains 5 examples. So what we are doing is we passing each image through the embedding through our network and generate the embedding this. So once we have the centroid, so once we have centroid for each class, and if we want to compare the new image is coming, and then that image will be assigned based on the distance calculations. And after that distance calculations, in order to calculate the probability of that class, that image belonging to any class, what we are doing is we are taking the negative of that distance and we are applying the softmax. Why we are taking the negative? Because we want distance to convert into the similarity image. So the larger the negative number, the closest that image within that group. So hope this is clear to right. Is he listening to me? I don't know.
The centroid means the centroid, like the embedding centroid, right?
Right. So okay.
Ravinder, one last question. That hard negative, semi-hard negative, what is the example for that? What is the distinction between hard negative, semi-hard negative?
Okay, let me give you a fictitious example. So assume that we are having some twin. So the twin will be hard positive example, and hardest, I guess, the positive example, and the hard negative will be something that might be some cousin that looks like the same thing, but that is not similar to that person. So I mean, uh, okay, no, okay. So let me let me rephrase it. So the
Okay.
hard negative is that twin, because that twin is not so that twin is the hardest negative. Those are similar but not the same. And the other thing is that hard positive. So if I talk about the hard positive is that if there are pictures of that person that you are thinking that is matching with that twin, but that picture is not that twin. So I mean, there are, if you see that, so hard twin and hard positive and hard negative are something that are very equidistant. So we cannot say that this is that person or not. I mean, feature wise. So when we are generating that embedding, so it is hard to distinguish, because that thing is lying between that. So I guess so. I don't have that.
It's fine. It's fine.
So
It's
let
fine. No
me.
problem. No problem. I will look at it. No problem.
Sure.
Yeah, I will look at it. Thank you, Ravindra. Thank you.
Yeah, welcome. So we had. I was explaining. I was explaining for Sankalp. So Sankalp, you are clear with that. So here we are doing that minimization objective. So our objective, this is a negative log probability. So what we are doing is we are taking the sigmoid. So we are calculating the probability, and we are taking the sigmoid of that thing, and after that sigmoid, if we take the log, then we will achieve this objective function. So this is basically the negative log probability. So why we are calling it, this is why we are calling it negative log probability, because if you take a log of this, you will reach to this equations. Hopefully this is clear to you now, because these things are represent. So ck is here the centroid, and this embedding of the image that we are comparing with that centroid. So if you see, this is ck, so this is for c2, and this is the function that we are applying. So if you see this, so we are calculating it, and then taking the negative, and then taking the taking it overall, taking the exponential and the sigmoids of that stuff. Hope this is clear to you now, right?
Yeah, he typed yes in the chat.
Okay. Yeah. Thank you.
Yeah. Thank you, Ravinder.
So any
Thank you, Nikhil.
question? Yeah. Yeah. You're welcome. No problem. So can we wrap it now? I mean, it's nearly 11. So we are hitting
Sure.
that
Let's
numbers
wrap
of
it up.
hours. Okay.
Yeah, thank you,
Yeah.
everyone.
Thank
Good.
you.
Have a good night. Yeah.
Thank you. Thank you.
Thanks, Ravinder and Nikhil.
Yeah. Thank you. Thank you, everyone.